Hey, what's up, you guys? Welcome back to Engineer with Musa. This is Mohammed. Today we're going to go over another static engineering problem, and we're going to be talking about distributed loads on a cantilever beam. So let's jump right into it. I'm going to go ahead and paste the problem in here again. Cool. So this is the problem we're given, and we're asked to find the reaction. So find the reaction at the support. And we do this by using Newton's law and equation of equilibrium, and I'll kind of walk you guys through it. So let's just go ahead and start. First things first, we're going to use the free body diagram. And we'll go ahead and draw our beam again. And we're going to draw our distributed load, which is 15 kilonewton meter on the left hand side and 5 kilonewton meter on the right hand side. And it kind of descends linearly like so. Cool. And then we're going to draw the anticipated reaction. So we're going to call this left hand side point A. So we can draw the vertical force over here to be AY. We can draw the normal force over here, or the horizontal force, to be AX. And because it's a cantilever, we're going to have a moment, and this end over here is fixed, so we know that there'll be a resisting moment as well. And so we'll draw that like so. I'll call that MA. So a really important thing here to do is to turn this distributed load, drawn in green, into point load in order to simplify our equation. So we know that this distributed load can be broken into two different types of loading. I'll go ahead and dash it out. So we have this rectangular shape down here, and then we also have, this is one of the distributed loads down here, and then the other one is up here. So this distributed load can be turned into a point load by saying we have 5 kilonewton times the length of the beam, which is 12 meter. So 5 times 12 is equal to 60, and it occurs right at the center. So I'll kind of make this a little bit bolder. So this would be 60 kilonewton. And that takes care of number 1. And for number 2, it's going to equal to 15 kilonewton times the shape of the triangle, which is 1/2, base, which is 12 meter, times the height, which is 15 meters. So we have, essentially, we're drawing the 12 meters down here, 15 kilonewton meter over here, and then this is how you turn a distributed load into a point load, which is going to be also 60 kilonewton. But the difference here is that it's going to be 1/3 of the distance from the left hand side, as opposed to halfway. So 1/3 times 12 meters is equal to 4 meters. So it's going to be somewhere over here. So there we can say our second distributed load, 60 kilonewton, is 4 meters away. So now I'm going to kind of get rid of those two. And now we can simply start drawing or start writing our equations of equilibrium. So we can say that the sum of the forces in the y direction is equal to 0, given that up is positive. And we have AY right here minus 60 kilonewton minus 60 kilonewton is equal to 0. Therefore, AY is equal to 120 kilonewton. And this is positive. Then we can write sum of the forces in the x is equal to 0, given that right is positive, and we can say that AX is equal to 0, so there's no horizontal force. And last but not least, we have sum of the moment about point A is equal to 0, given that counterclockwise is positive. And we can say we have MA, which is our moment right here, minus 60 times 4 meters minus 60 kilonewton times 6 meters, since this is located 6 meters away from each half. To 0, and then therefore MA is equal to 60 kilonewton. So 60 times 4 is going to be equal to 240 kilonewton meter plus 360 kilonewton meter. Therefore, MA is equal to 240 plus 60, which is 600 kilonewton meter. And so if you were to redraw your kind of beam setup, hope you enjoyed, and see you next time.